In this video, we are going to solve the equation m times 4m squared plus n plus 12 equals 3 times p to the power n minus 1, where m and n are positive integers and p is a prime number that is greater than or equal to 5. Before we move on, don't forget to give a like, subscribe to our channel, and turn on post notifications. My first step would be to expand both sides, so we have 4m cubed plus m squared plus 12m equals 3 times p to the power of n minus 3. Then I'm going to move the minus 3 to the left, so we have this equation. Notice that now the left can be factorized, so it can be factorized as 4m plus 1 times m squared plus 3, and that equals to 3 times p to the power of n. If the product is just equal to a prime power, or I should say a perfect power of a prime, which only contains one prime factor, then it will be much easier. However, we have a 3 on the right, so we have to settle this first. To do this, I'm going to consider the fact that 3 divides the product on the left. Since 3 is also a prime, then either we can say 3 divides 4m plus 1, or 3 divides m squared plus 3. For the first case, we can quickly say that m is congruent to 2 mod 3, while for the other case, we know that m squared also has to be a multiple of 3. That means m itself is a multiple of 3. Then we can let m, say for the first case, equals 3k plus 2, some positive integer k. Then for the other case, I can write m equals 3k instead. And for each case, I can replace the equation, like for each m, I can replace by either 3k or 3k plus 2, and try to simplify the equation so that the product on the left is equal to the perfect power of a prime number. For the first case, let's try m equals 3k plus 2. Then the equation becomes, for 4m plus 1 is equal to 12k plus 9. And then for m squared plus 3, it will be 9k squared plus 12k plus 7. And that equals 3 times p to the power of n. So simplifying by dividing both sides by 3, we have 4k plus 3 times 9k squared plus 12k plus 7 equals p to the power of n. Now notice that for each part of the product on the left, 4k plus 3, 9k squared plus 12k plus 7, given that k is a positive integer, they are both larger than 1. So that means each of them should also be a power of the same prime number, p. And in particular, one of them must divide the other, or for some special case, they are equal and they divide each other. But from the structure of the two parts of the product, it's clear that 4k plus 3 is smaller than 9k squared plus 12k plus 7 when k is a positive integer. So we can say 4k plus 3 divides 9k squared plus 12k plus 7. So I'm going to try to solve for k from this divisibility relation. From this, I'm going to multiply the multiple so that when divided by 4k plus 3, we will have integer coefficients. To do this, I'm going to multiply by 4, so 36k squared plus 48k plus 28. When I divide this by 4k plus 3, the quotient will have integer coefficients. Indeed, the quotient is going to be 9k plus 5, and then the remainder will be k plus 13. So I can immediately say that 4k plus 3 divides k plus 13, and using the same trick, multiplying the multiple by 4, I can further reduce the multiple by 4k plus 3, and so we have only 49 remaining. But this is good because that means 4k plus 3 have very few choices, either 1, 7, or 49. And for 1 and 49, we can reject them because we won't have any positive integer solution. But for the remaining case, we know k equals 1. So given that k equals 1, because we have assumed that m is equal to 3k plus 2, that means for this case, m equals to 5, and to solve for p and n, we have to go back to 4m plus 1 times m squared plus 3. Equals 3 times p to the power of n. And simplifying, we have p to the power n to be equal to 196. But that's not going to happen because 196 is 14 squared. It's a power of a composite number, but not a prime number. So no solution for this case. Then we have to go to the other case, which assumes m to be equal to 3k for some positive integer k. From this, we can proceed by writing that as 12k plus 1 multiplied by 3k all squared plus 3 then simplifying, we have 12k plus 1 times 3k squared plus 1 equals p to the power of n. Now for this case, we can't quickly decide which is the larger part of the product, but still each part of the product on the left is greater than 1. So that means they should also be a perfect power of the same prime. So we can say either 12k plus 1 divides 3k squared plus 1, and this happens when 3k squared plus 1 is the larger part of this product. So from this we know this can only happen when k is at least 4. While for the other case, that would be the other way around. 3k squared plus 1 divides 12k plus 1, and this happens when k is between 1 and 4. So for the case at the left, I can use a similar trick like before, but this time I'm going to multiply the multiple by 48 so that I have 144k squared plus 48, and to divide, I'm going to write that as 12k plus 1 times 12k minus 1 plus 49. So then this product, 144k squared minus 1, can be removed. And therefore, 12k plus 1 again divides 49. So those options appear again. We can put away 1 and 7. They do not provide positive integer solutions for k. And for the remaining case, k equals 4. So this time, m has to be 12 because it's equal to 3k, and that means 4m plus 1 multiplied by m squared plus 3 equals 3 times p to the power of n. So 49 times 49 equals p to the power of n, and the only option is p equals 7 and n equals 4. So now we have one solution set. And finally, if k is between 1 and 4, then we can try them one by one. K equals 1 is clearly wrong. And for k equals 2, the divisor is then 13, and the dividend is 25, wrong. And when k equals 3, we have 28 divides 37, wrong again. Of course, when k equals 4, we have a solution, so we do not have to check. The dividend and divisor should be equal when k equals 4. So altogether, the only solution for m, n, and p is m equals 12, n equals 4, and p equals 7. So this is the final answer. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.